Okay, and I'll share this. Okay, so this was the material we did on the last video, yesterday's video. And I did make a mistake on that. You'll see there's actually 3 different videos. They're all kind of, I couldn't splice them together in time. So I made a mistake in the second video where I'd said the water, I said the water didn't react, but then I actually used the voltage for the water. And in the third video, you'll see that it's been corrected. So this actually is the correct answer down here. And if you watch all 3 videos, I think that'll make sense if you see that. Okay, so let's talk about applications of this stuff we're learning. So we've learned about batteries, and there's a whole section on batteries, which I'll talk about in a bit. But the main thing I want to cover from this is 3 main applications. Okay, so 3 main applications. And the first one is on spontaneous reactions. So spontaneous reactions are ones that will occur without any assistance. So they would be a step down reaction on the table, and they would also have a positive E0 value for the cell. And we talked about what that means in the previous videos. So, so some of the applications or things we see them in, the main one I think that I would like you guys to know about that I think is really important is the process of corrosion. Okay. So corrosion can take many different forms. The most common one I think we would associate corrosion with would be the corrosion of iron metal. So this is where iron is oxidized. And when it gets oxidized, it's more commonly called rust, or the rusting process. And there, you can actually cause corrosion of many different metals, by the way. So aluminum can be corroded, nickel can be corroded. And you've seen that in those battery questions we did where one of the electrodes got smaller, was being oxidized. So that actually would be called corrosion. It's corrosion of that metal. But generally with corrosion, I think for most people, they think of rusting. They think of iron being oxidized here. So I'm going to give you the general gist of what that is and then how we generally prevent it. So that's part of today's lesson. And then the other part of today's lesson, we'll be looking at applications of electrolysis, which is what the last few videos were on. And those would be reactions that are not spontaneous. Those are ones you need a battery for or some kind of power source for. So the first one's corrosion. This is a natural occurring reaction, and it's between iron. So let's see if we can find iron on the table, and iron's solid. And that's down at negative 4.5 volts. Okay, and that is, if you create a little table for oxidation and reduction, notice that we're making iron the reducing agent, so we're going to oxidize it. And then so we need to know, well, how does iron actually oxidize in the first place? So let's say you had a piece of iron. And this iron is to be oxidized. Well, the actual oxidation process, before we knew all about like electrons being transferred back and forth, most people just recognize that if you leave iron out in oxygen, it rusts. And so that's just something that people knew from a long time ago, well before we sort of know what we understand as modern chemistry. And so if you get iron wet, so let's say a droplet of water on there, and that water, obviously it's in the atmosphere, so maybe a piece of iron got rained on. And then you have oxygen gas in the environment, and that comes together now, you will get corrosion occurring. So what we're going to look for is the reaction that involves oxygen here. And there's a few of them, if you got to be kind of careful here. I'm going to look for oxygen being reduced under neutral conditions. So this is the water reaction that we've been looking at for the electrolysis of solutions a little bit here, if you look at the last few videos, at 0.82 volts. If you can find that on your table. And that's the one that's half O2 plus 2 H pluses And notice it says 10 to the minus 7 molar. I have to squeeze in the electrons here, plus 2 electrons. Okay, but what I want you to pay attention to is you have oxygen. Okay, so you have oxygen. Okay, and now of course you can see that this oxygen is in the presence of H plus at 10 to the minus 7. So that would be under neutral conditions. So pH 7. Okay. And why that's important is you see the molarity there. That implies that the oxygen and the hydrogen are coming together in a solution. So this is where the raindrop is important here. You need some moisture. Even in the morning, if you wake up in the morning and you look at the grass, you'll see the dew on the grass. So any level of water will allow this to occur. And so what happens now is the oxygen goes into the water and it gets reduced. So what does it turn into if it gets reduced? Well, you'll see it gets turned into water. So you have H2O on that side. And in fact, if you think about the previous videos, that's the reaction we looked at for the oxidation of water, if you've watched those videos. And then of course the iron now, so the iron is being oxidized. So this is higher up, so it's gonna go that way. The iron is being oxidized. It's making Fe, I think it's 2 plus here. Yeah, 2 plus, and 2 electrons. So that's a spontaneous reaction. So the iron is going to break up into iron ions. And this reaction now doesn't actually help us understand why rusting is occurring though. So we can see that the oxygen is being reduced, the iron is being oxidized. But what is rust? Like what is rust? Well, rust is Fe2O3, so iron oxide. And then usually it's actually a hydrate. You actually get water molecules attached to it. And depending on the number of water molecules attached, the rust can be different colors. So you can get like a dark red rust or an orangey rust. And it all depends on the type of hydrate you have of the iron oxide. Okay, but once again, doesn't really explain like where I see the Fe part of it, but what about the O part? Where does that come from? And so what we're gonna have to do is take a look at the water reaction again. So this is the confusing part, but hang in there. You might remember when we balanced the redox reactions earlier on, we looked at balancing them under acidic or basic conditions here. So this is the reaction you see on the data table. This is the one you look at. It's at 0.82. And that is the reduction of oxygen. But what I'm going to do is I'm going to write this from the perspective of hydroxide, not from the perspective of H pluses. Because if you think about it, if this reaction goes forward, which it's supposed to do here, what would happen to the amount of H plus? Well, the amount of H plus would have to go down because it's a reactant. But if you decrease the amount of H plus, that means you must be increasing the amount of hydroxide ions. So this reaction, although it shows producing water, it also produces hydroxide. So this is where kind of like acid, base, and redox kind of come together. It's a bit confusing. So I'm going to balance this reaction looking at it from the basic perspective. So I'm going to use my water reaction just like I did in the redox questions when I balanced them. And what I'm going to do now is add a 2, a 2, and a 2. And I'm going to look at this equation from the perspective of hydroxides. So remember, H plus is going down because it's a reactant. So OH should be going up. So if I add these things together, that should cancel. And now what I would have is half O2. And then I've got 1 water there and 2 there. So 1 water here plus 2 electrons going to form 2 hydroxides. And they would initially be at 10 to the minus 7 molar, like before the reaction goes. Now what happens is the H plus goes down because it's shifting to the right, which means the OH concentration is going up. So this reaction is actually producing hydroxide ions. And if you look on your, so this is sort of this question ties in 3 different units, actually 4 different units because it's also equilibrium, but it also ties in the solubility chapter now. Because if you look on your data table for iron and a hydroxide. Where is it here? Iron 2 hydroxide is, and you can actually also get Fe3 plus being formed. So you can actually get different oxidation states. But then you have Fe 2 plus. Let's do that again. You have Fe, if it's the 2 plus, want to be OH2 and FeOH3. And what happens is these chemicals, they have very low solubility. And so they start to form a precipitate. And then those precipitates will undergo further redox reactions. And eventually you will wind up getting your Fe2O3. So I'm not going to get you to memorize all the reactions here, but I would say you should know this reaction. You should understand that is what's happening as the oxygen is being as it's being reduced, and of course the iron metal is being oxidized here. So what happens is you'll start seeing in the metal, you'll start seeing these little holes appearing, little pits, and that's where the iron metal is starting to be used up. The other thing I wanted to mention here was the effects using Le Chatelier's principles to understand how you could make this reaction go even faster, and where, and more importantly, where it would go faster. So, for example, this reaction here, this one here, it's when this is 10 to the minus 7, which is purely neutral. And if you remember from the acid base chapter, when it rains, sorry, Dean just joined us. Hey, Dean. So this reaction we start with here, the OO2, that's at 10 to the minus 7 molar. So that would be under neutral conditions. And when it rains, remember the rainwater passes through the atmosphere and comes in contact with CO2, which means that rainwater itself, its hydronium concentration is not 10 to the minus 7. It's actually higher than that, which, if you think about it, that actually would increase the amount of H plus, which would want to drive the reaction even more in the forward direction, which means that rainwater would actually cause this reaction to speed up because it's more acidic. And if you apply that to acid rain, like in cities where you have high levels of hydronium ion, areas like, for example, some of the big cities in China, some of the big cities in India, you have rainwater that's quite acidic. And so the actual reduction of O2 is even higher. It's more favored. It's higher up on the table. Which means that the rusting process in those cities is much higher, which means more damage to infrastructure, more damage to homes, and just general needing to be repaired and stuff. So this does tie into a lot of different chapters. You can see we've got equilibrium, we've got redox, we've got acid-base chemistry, and also solubility chemistry tied in here. So it is kind of a neat topic, but more practical for you guys is how do we prevent rusting? Like what's sort of the ways to prevent rust. So how do we actually prevent the rusting process from taking place? So, for example, most vehicles now are made out of different alloys and different materials. So it's unlikely you're driving around in a purely iron car, but a lot of the parts in the car are iron. There's various parts of the frame that are made of iron. If you have a bicycle, there's definitely probably some iron in there. And if you use nails and all those sort of things, there's nails that have iron in them. So how do we prevent rusting? Well, the number one way, I think, for most things is we paint the surface. So if you have, I don't know, so this is Noah here, and I think we have one more joining us. Hey, Amanda. And let's say this is his big iron car. And so if he doesn't paint if his car is not painted, then the entire car would rust out. So generally we paint it in a material, and big yellow truck for Noah, and that's going to protect the it's going to prevent, think of it this way: if you have a big chunk of iron and then you've got a layer of paint over top of that, then the O2 can't come in direct contact with the iron. So that's one way to prevent rusting. The other way to prevent rusting is a process called galvanizing. And this is actually really important, as I found out, if you're building a fence, say. So if you're outside and you're going to build something that's going to have to withstand the elements, especially on the coast here. I had a neighbor a while back who had built a fence out of housing nails that are nails that you would use inside your house. So basically, if you were nailing 2x4s together inside the house, and those are just iron nails, basically. But the galvanized nails, what they are is a nail that they've dipped in maybe zinc or magnesium. And what happens is they dip it in there and you get a layer. The zinc and magnesium actually, they form an oxide, which could be like a zinc oxide layer. And which really is the corrosion of zinc, if you think about it. But what's the difference between zinc oxide and lead oxide is that zinc oxide is very hard, actually. It's a really tough material. Whereas lead oxide is, sorry, why am I saying lead? Iron oxide. Sorry, guys. We're resting here. Iron oxide is very brittle. If you've ever seen any rust on a vehicle, if you just touch it even, it just brittles and it breaks and falls off. So the zinc oxide layer performs a really strong layer, which once again, kind of like painting, prevents the nail from being coming in contact with the oxygen. Now, the added advantage is if you're hammering a nail into some wood, so let's say you're putting two pieces of wood together with your nail, then the nail, as it moves through, if you just painted your nail, then as you'd hammer the nail through the wood, the friction between the wood and the nail would just peel the paint off. So the zinc oxide layer is quite strong, so it goes through that. But obviously, if you, I mean, you guys are really smart students and stuff, and maybe you don't have any experience with this device I'm drawing here, which looks nothing like the actual device, but this is my hammer. So this is the device used to hammer a nail in, called a hammer. And of course, if you hit the top of a nail with a hammer, big metal hammer, you can chip parts of the zinc oxide layer off. And that's actually the most vulnerable part of the nail now. And over time, rainwater would get in there and corrode the nail from inside. And then, of course, once the nail's corroded, the boards can come apart again. So what's a good idea is to repaint the surface after you're done. So after you nail things together, maybe put a coat of paint on it or some stain on your fence, and that'll help protect it. And the last thing I want to talk about preventing this process here is actually from a true story. I had tenants downstairs when I first moved into my place. And just give me 1 second. Sorry, there we go. I had tenants downstairs that were good friends of mine living down here, and one of the tenants came and she said, when I'm showering, there's mud coming out of the shower, and I didn't know what she was talking about, and so I went down there, and sure enough, I turned the tap on, and there's mud, what looks like mud, coming out of the shower, and I couldn't figure out what was going on. But I took the ceiling tile up from downstairs and tracked all the plumbing pipes, and I eventually found there was a room, a hidden room. It was sort of a drywalled in. I never knew it existed in the house. And inside there was a hot water tank, and there was another hot water tank in the other part of the house that was providing hot water to the upstairs. So upstairs there was no mud coming through the taps. It looked like normal water. It was normal water, but the hidden hot water tank, hiding behind the wall here, it's a hot water tank. And what you'll see on the hot water tank is there's usually a pipe coming out one end, a pipe coming another. It's a big bolt kind of in the middle here. And cold water comes into the tank this way. And then there's a bunch of heaters in the tank, and it heats up the water. And then the hot water comes out the other pipe. And if you hold on to the pipes, you can feel the cold water and the hot water. And these tanks are basically just iron tanks. They're just made of metal. So there's iron in them. And what happens is the iron will rust over time. Now, the reason that you don't get rust right away is that this bolt actually is attached to a long rod that goes into the tank. And this rod is usually made of magnesium or some other metal. And they call this the sacrificial anode. Kind of a sad name. So sacrificial anode. So what's the purpose of this magnesium rod? Well, if I look at my the data table I used above, I had reduction and oxidation. And I had the O2 reaction way up here, and that was going that way. And I had the iron reaction going that way. And if you look at magnesium, it's actually below the iron. And what happens now is as the water comes in with oxygen in there, oh, hey, Brendan, as the water comes in with the oxygen in there and it's about to oxidize the iron, it now has another metal it can choose from. And so the magnesium being lower is preferred. It's a preferred electrode. And what happens is the magnesium winds up getting oxidized as opposed to the iron. And so what happens over time is that this magnesium rod is getting oxidized, so it's getting smaller and smaller, and eventually it just vanishes. It's just completely used up. And once you use up all the magnesium, then you start getting iron being oxidized. And that's troubling because, of course, the tank itself is structurally designed to hold this water in there that's actually quite hot. And it's got pressure coming in from the city. And then, of course, when you use it, it pulls the water out. But of course, if you start to degrade that tank, then it will rupture, burst, and leak, and could cause problems and stuff. But the other thing is you actually get rust in the water, which is gross, but not dangerous to you. And in fact, some students asked me last year, what about the magnesium ions? And the amount of magnesium you would get when you're showering is quite low. And magnesium ions are not exactly harmful to us, at least in the quantities you would be receiving them. You don't want to ingest huge amounts of magnesium, but some people do have them as vitamin supplements. Okay, so that's called a sacrificial anode, or what's the other name for that? Galvanic protection. And oops, sorry, I'm trying to let Brendan in here. If one of you guys knows Brendan's number, maybe let him know I'm trying to let him in. Oh, he's in now, I think. So he's here. Okay, so that's our big talk on rusting. Okay, so actually one more thing on that big thing here is many boats, actually, big Navy boats and stuff. So the SS Deanator. There we go. He's got big guns. And so if you look on the bottom of these boats, you'll actually see these strips on the bottoms of the boats. And every like 5 or maybe 10 years, these boats go into dry dock, and you'll see the workers taking these strips off and putting new strips on. And these strips are actually made of magnesium or some other metal that can be oxidized. And the whole idea here is you want the hull of the ship, which is mostly made of iron, you want the hull protected. So these strips actually provide protection against the hull. And going back to the hot water tank thing, once that bar is gone, then the hot water tank is basically considered to be not good. And so many hot water tanks, if you go to like Home Depot, it'll say like a 5-year hot water tank or a 10-year hot water tank. And that would be dependent on the amount of material that they've used for the sacrificial anode. And of course, the more material they use, the more expensive the hot water tank is to buy. Okay, so that's that. So those are all spontaneous reactions, all involving the rusting process. So I wanted to finish off by talking about electrolysis reactions, or non-spontaneous reactions. So these are the reactions that do not happen on their own, okay? And once again, if you don't have a data table handy, you really want to get one here for this, because this is a bit on the confusing side. Yeah, I'll use that one. Guys, okay, there we go. Okay, so let's just do two brief examples of where we see this technology being used here. Okay, So the first would be if you are trying to plate something. So we refer to this as electroplating. And this is done quite often with electronics. I know with like HDMI cables, you can buy like, cheap ones or more expensive ones. The more expensive ones, generally, they claim to be coated in gold. The wires are coated in gold, which is, I think, is actually is better for electronic signaling. But I think from most the studies that have come out, the level at which the data is being transferred is not being impacted by this sophistication. Maybe down the road it might prove to be useful, but I think you can get away with some cheap HDMI cables as opposed to the more expensive ones. But the idea is that they've plated the metal in a more expensive metal. So let's say that, and I'm going to use the example I used in class yesterday. So for those that were here, this might be a bit of a review here. Let's say that you go to a country and you buy some jewelry, and they claim that the jewelry is like real silver or something like that. So expensive metal, and then you buy it and take it home, and then you wear it for a while, and you realize it's not silver. And the question is, well, how do they trick you? Like, because maybe maybe you really did believe it when you first looked at it. So one way they can do that is, let's say I actually bought some onks when I was in Egypt, and I knew they were not real silver, but they were just a little souvenir I bought, and so they're kind of shaped not like that at all, actually. But anyway, let's just say a piece of jewelry, and it's made of a cheap metal. So something that would be worth very little in terms of its value, and but I want to make it look like it's valuable. I want to make this thing look like it's worth big bucks. And so what I'm going to do is I'm going to attach a wire to it, and attach it to a DC power source, so a battery or electrochemical cell. And over on the other side, I'm going to have a rod of another metal that actually is quite expensive, or at least it makes it look like it's an expensive metal. So this would be in a solution. Okay, and one of the metals that work quite nicely here is nickel. Nickel actually has a fairly lustrous quality, which does make it look quite similar to silver when it's on just looking at it from a distance. And what I'm going to do here is I'm going to put some nickel ions in solution. So my goal here is to take this cheap metal jewelry and coat it in a metal that looks nice, makes it look like it's worth more than it really is. So my goal here is to move the nickel ions onto that surface. And what I want to do is I want to coat it. So I'm going to use a different color here. I want to coat it. Whoa, that's my daughter using fancy colors. Let's try this one. I want to coat it in this nickely material, which is not orange, but just to kind of illustrate. I want to coat it in that material. So I want the nickel ions to move that way. So how do you think your battery would have to be hooked up? Like, would you want the negative end or the positive end here? Or would you want the negative end or positive end here? Or maybe a better question would be, which one would you want to make the cathode and which one would you want to make the anode? Well, I'm trying to make the nickel ions turn into nickel metal. That's my goal. So what I need to do is I need to reduce the nickel ions. I need to turn them into nickel metal, which means I have to give them electrons. So I need the battery to hooked up in a way that causes the nickel to get reduced. So I need electrons flowing into the jewelry, which means I need this to be the cathode. Okay. And I need the other side to be the anode. So in order to do that, the batteries would have to flow out of the left side of the battery. So I need my negative end there and my positive end here. Okay. And now what would happen is electrons would flow into the jewelry, the cheap piece of metal, and they would be willing to give those electrons to anything around it, which would be the nickel ions. and the nickel would plate onto there. And then once I get enough plating on there, I could take that piece of jewelry out and put another piece of jewelry in. But what's going to be happening at the anode, do you think? Well, as the battery pushes electrons into the jewelry, it's pulling electrons out of the nickel metal. And so what would happen is the nickel metal would oxidize to form nickel ions. And so what would be going on here is that as long as you provided enough nickel ions to start with, and you had a nickel bar, the nickel bar would just keep oxidizing and producing more nickel ions, which could plate onto your jewelry. So you could run this many, many times and plate many pieces of jewelry. Or if maybe you weren't trying to rip someone off, you were just doing this because you needed to coat something in another metal, such as the HDMI cables we talked about, that could be used this way. Now, the actual reaction might trick you a little bit, because if you look at what's going on here, you have nickel being reduced to form nickel metal. But then you have nickel metal being oxidized to form nickel plus. Now, of course, the voltage on this is the same, because it's the same reaction. I'm just looking it up in the book here, negative 2.6. So this reaction is negative 0.26, right? But you would have to flip one of them, which means the other one would be positive 0.26. So the E naught for the cell would look like it's 0. But it's important to understand you would have to apply some voltage to this thing to make it go. And so it would not happen on its own. So you need to have some voltage to have this occur. Okay, so that was something I covered yesterday. So we've done rusting today. That's a spontaneous reaction. So that's one that happens on its own. Don't need any help with that. We talked about ways to prevent rusting. So that's like painting, galvanizing, or electroplating. Using a sacrificial anode. And then right now we talked about non-spontaneous reactions using electroplating to move a metal onto another metal surface. So the last example I wanted to use today was a process referred to as electrorefining. Oops, electrorefining. Okay, and electrorefining is used many times when we try to purify a metal that we've extracted in the form of an ore. So sometimes when we create a mine to mine some precious metals, you can't just dig down and find a big chunk of gold. Like there's no nowhere you just go, oh look, a giant piece of gold or a giant piece of copper or a giant piece of aluminum. It's usually in the form of an ore where it's being mixed with other chemicals. And one way to separate those chemicals is a process called electrorefining. So let's use copper refining here. That works out. That's a pretty easy one to draw. So let's say we're trying to purify copper. So we're looking at a mine that's mining for copper. And so what they can do is they can kind of do what we did above. They have a big tank of solution, and maybe they stick their ore, giant piece of ore, not like an ore, right, or an ore, but a ore. So big chunk of rock, and they attach a wire to it, and have a DC power source. And this ore though is copper ore. Okay, so it's copper, which means it's primarily copper, but there's impurities in the copper. So you might have trace metals in there that you don't really want to have. You want to try to make it pure. And at the other end, you have a wire attached to a pole. And this could be carbon. It could also be copper if you wanted it to be. But generally this happens in a big, like giant factory, and this would be attached to a crane. So the crane would be able to lift the ore out and lift the copper or the carbon rod out and transport it. So my diagram of a beaker doing this is not really like a true factory that would do this, but it gives you the same kind of idea. So this would be a solution. So solution here. Okay. And what you're trying to do is you're trying to get the copper from the ore onto the carbon electrodes. You're trying to purify all the copper that's in here and move it over there. So what the company does is they actually put their own copper ions into solution. So that would be, they would have to spend money to do that. So they've got this copper ore, but they're actually putting money into the process by adding copper ions to solution. And what they're trying to do is move the copper over. They're trying to go that way, just like we tried to move the nickel ions over. So we have to hook the battery up in the right way. So we want the copper ions to go over here, even though these are the copper ions from the company. So what happens? Well, the battery has to be hooked up in a way that makes that work, which means we need to reduce the copper ions. So this must be the cathode. And this must now be the anode, which means the electrons have to flow from anode to cathode. So that's the electron flow in which the electrons have to move, which means the negative end of the battery has to be here, and the positive end of the battery has to be here. So let's say in this copper ore, this impure ore, you have these chemicals I'm gonna write down here now, which are let's say you have some magnesium, so little pockets of magnesium, maybe some aluminum, maybe some gold, tiny bits of gold, and maybe tiny bits of silver, and just say zinc. Okay, so you have this ore that's mostly copper, but it does have these trace amounts of chemicals that you don't really want. You want to get rid of those and just have pure copper here. So the company adds copper ions to solution, and then what they do is they turn on the battery or the big power source, and they just allow this to go to work. So what we have is a little table here: reduction and oxidation. So we have copper ions that the company added. So they added their own ions to the solution that are going to get reduced at the cathode. And then, and they're also higher than the water, so the water won't compete for it. And at the anode, you have all these metals. So I'm going to write these metals down as they appear. So basically, I have copper, metal, and then I need to list these things here. So where's magnesium? Magnesium is pretty far down. Aluminum is just above the magnesium, and zinc is just above that. So I should probably written a bit better. And then I've got silver above that, and then gold is really high up. It's really hard to oxidize gold, which is why they make most expensive jewelry out of gold, and then silver after that. Okay, so what happens then? Well, the copper winds up getting reduced. We've already kind of determined that. Okay, so that gets reduced. But then as far as the other 6 chemicals, magnesium winds up getting oxidized here. So what would happen is you would get magnesium ions in solution. And then, of course, let me just choose an appropriate color. Yeah. So what you would see, though, is a layer of copper forming around here. Now, of course, this copper is the company's copper. They put this in, so this is them losing money right now. But what you'd have is magnesium ions in solution. And of course, as soon as you make magnesium, now you have 2 different chemicals that could get reduced. But we know from the table the thing that's highest up will always get reduced. And this actually is why the company is putting their own copper in. What they don't want to do is transfer the magnesium ions onto the cathode. So they keep adding copper here. And so they would notice the solution is becoming less blue over time. So they just add more copper ions. And then once all the magnesium is gone, remember just trace amounts of it, then the aluminum would start to undergo oxidation. And now what you'd have is you'd have 3 chemicals in solution. You'd have magnesium ions, aluminum ions, and copper ions. Once again, copper is higher than the other 2, so it still gets reduced here, okay? And then once again, you would run out of aluminum. And then the zinc ions, they would get oxidized. So you get zinc ions being formed. But just like the other 2, they're still below the copper, so they're kind of ignored at this point, okay? Now, once you've gotten rid of all your trace ions, these here would be pockets now. They'd be like holes. It would almost look like Swiss cheese. And so you'd have these holes where the chemicals used to be, but they've all been oxidized into ions. So now what comes is you have copper, silver, and gold left in the ore. So you have the copper ore that you want, and you have these other trace elements that are higher up on the table. So now what would happen is at the anode, the copper now would undergo oxidation. So now you get copper being produced. And that's actually the copper that comes from the ore. So really at this point, the company would stop adding copper ions to solution. And what you would notice is that this electrode would get bigger and bigger and bigger. And of course, the ore itself is mostly copper. It might be like 80% copper. So now the copper ore really starts to get oxidized here. You'd see big chunks of it disappearing. And you get bigger and bigger here. Now, at some point, the mass of the copper would get to a point where it might be too much. And the crane would lift this off and get, maybe melt the copper off and purify it, send it melt the copper off and then send it to the company that needs it, sells it to the public. And then what happens is once the copper ore, though, once all the carbon is gone, once all the copper is gone, so let's say the ore is now gone. The problem is you have the gold and the silver ions that are trapped, or sorry, gold and silver atoms that are trapped inside the copper ore. Once the copper ore is gone, these metals are going to be free in the solution. So you're going to have bits of gold, bits of silver, and they're going to be in water. And of course, they're way more dense than the water is, so they're going to they're going to sink to the bottom of the container, and you get this sludge at the bottom. It would look kind of like sandy stuff, kind of things at the bottom here, but it'd be very shiny, sandy stuff. And so this wouldn't be garbage, obviously. They would probably sell this to another company that would purify the gold and the silver, or maybe in the factory they have a way of doing that too, to purify that out. So the copper metal, the copper ore, the metal in the ore can be extracted using electrorefining. You do get a solution of other ions, so you want to be really careful that these ions don't wind up getting reduced. And that's why the company adds the copper ions to start with. As long as you have something higher up than these other ions, that's always going to wind up getting reduced before those ions do. So this is a process whereby you can purify a valuable metal, and you also get trace amounts of expensive metals that could be used for other companies, the electronics and stuff. Okay, so I'm going to stop there, and I'm going to stop recording. And I wanted to quickly go through with you guys some stuff that you're not going to have to know. So if you have your book handy, maybe I'm going to stop recording this now. So let me just stop this for a second. Here, stop recording.